Before we take an AI model or a data pipeline to production, we're faced with the decision on how best to productionalize that asset. Leading up to this decision, we're often already exploring things in Jupyter notebooks, and we may want to experiment with things like hardware accelerators and different code configurations in that same exploratory, interactive environment. The flexibility and interactivity could make this option better than alternatives like pipeline tools or even more custom orchestration frameworks that allow us to flexibly run, compute, and associated experiments. Of the many choices for how to experiment with hardware, code configurations, and productionalization options, this video will focus on Jupyter notebooks and how to expertly leverage them, including with accelerators, on the Google Cloud Platform. Even within this Jupyter option, we have a lot of ways, especially within Google, that we can set up and run our notebooks. On the more consumer, inexpensive side, we have projects like Google's Colab. This is certainly an option for us, including the Pro option, which gives us access to some accelerators, but there are at least another 6 major options to consider if we expand the picture to Google Cloud proper. One of those is a very small change to the first option, which is to run the Colab platform from the marketplace in Google Cloud, and ultimately that will back your Colab instances with GCP Compute Engine instances. The next option would be looking at the managed ways to run notebooks on Google Cloud, which is with Vertex AI Workbench, and specifically, we can look at the user-managed notebooks as well as managed notebooks. The key difference there being that the managed notebooks are run on Google-managed VPC networks and Compute, while the user-managed notebooks are run on Compute Engine instances right in our project. So there's a little bit more Google management of the service for the managed notebook, but we get a little bit more control and visibility in the user-managed notebook side. We'll walk through all these options shortly and then pick one to demonstrate how we can set up the notebook and also work through different code and accelerator configurations. Next up, we could use a more generic platform abstraction service on top of Compute like Kubernetes Engine. Now, there are really 2 flavors of this that may need to be considered independently. There's GKE Standard, which is a very normal and familiar way to run Kubernetes. And then there's GKE Autopilot, which is a more managed offering, including an obfuscation of the need to manage node pools. It's a bit of an opinionated approach that even changes the cost model, where we start paying for pods and no longer need to manage or pay for nodes. Then, on the very end of the spectrum, we have very low-level frameworks that we could use around Compute Engine. For example, we could use infrastructure automation services to provision notebooks on VMs. Now, of all these options, there are some important trade-offs, especially in terms of the fundamental trade-off between the level of abstraction and the level of control. However, we found that across these options, there are some sweet spots, and so we're going to dive into one of our favorite approaches in this video and show you how to set it up while also hinting at some of these other options as we go through. All right, so let's catalog all of these options. Colab, Colab with Marketplace, Managed Notebooks, User-Managed Notebooks, GKE Autopilot, GKE Standard, and Compute Engine. Now, before we start, we want to be able to understand and compare these across things like how easy it is to get started and use these notebook options, but also dimensions like machine configurability, enterprise controls and integrations, as well as things like hardware accelerators and their availability and flexibility. So really, we've already organized our options in terms of effort. For the Colab options, we have very low configurability in the consumer Colab offering. However, we do have, through the marketplace offering, a little bit more configurability. So, for example, if I go to Colab from the Google Cloud Marketplace and launch an instance, we can see that there is much more configurability around compute and GPUs. Now, in the Vertex Workbench, the managed notebooks also have some configuration, but note that there's a lot less flexibility as far as, for example, CPU architectures. It's more prescriptive around some of the hardware that's used, but we are able to size it and use some GPUs. The user-managed notebooks, however, the more traditional approach for notebooks on Vertex AI, do have more flexibility. For our machine configurability on GKE Autopilot, GKE Standard, and Compute Engine, we're going to be pretty good, but with Standard Kubernetes and Compute Engine in particular, we'll be exceptionally configurable since we're getting really flexible approaches for what kind of VMs we can use, and those are going to be run in the standard way with Google Compute Engine. Okay, let's add one more metric for TPU availability here. So in Colab, we have low availability. This appears to be something like TPU nodes. On the option here with the managed notebook, we really don't have that turnkey approach for TPUs. We'd have to configure that ourselves. CPU availability is sort of mixed based on the environment, and really there's a bit of a delineation between Google's consumer offerings and Google's business offerings here, as far as how much we can control and secure these instances and how much we can integrate them with other systems, for example, in Google Cloud. So while it may not be a home run in every aspect and does require some elbow grease, today we'll delve into using the GKE standard approach for running notebooks. One of the perks of this method is its vast configurability in terms of both accelerators and machine types. There are numerous extension points, but they do come with a small price tag in terms of the setup effort and management. As we hope you'll discover in this video, we believe this approach strikes a nice balance among the various trade-offs highlighted in this table. With our game plan set in stone, let's move ahead and create a Kubernetes cluster and then get some notebooks up and running to showcase important concepts. In our project, I'll navigate to Kubernetes Engine and create a cluster. Take note that it will recommend using an autopilot cluster by default, but due to the limitations mentioned earlier, we'll opt for the standard approach instead. The region and zone selection here is crucial. We'll discuss this in greater depth later, but one aspect we highly appreciate about the Google Kubernetes Engine approach is its flexibility with respect to zones and even seamlessly moving our notebooks across them. For example, if we wanted a small GPU, we could consider T4 and P4 options, but those are late 2010s double-digit nanometer architectures. Since it's 2023, let's go for something more thrilling, like the brand new 2023 5nm L4 chips. However, these chips aren't universally available in all Google Cloud zones, so we need to choose wisely. We could pick US Central 1A, for instance, to access the L4 chip and other options. That being said, once our cluster is up and running, we can easily shift to executing workloads in adjacent zones like US Central 1C and US Central 1F. This is particularly beneficial if accelerators are unavailable in that zone at that given time, or if you aim to minimize costs by utilizing preemptible TPUs. Ultimately, having flexibility around the zone can greatly improve cost savings and availability. Moving on, let's switch our zonal cluster to US Central 1A. This is merely where the cluster control plane will operate. We can run workloads in other zones within US Central 1 if required. The regular release channel will suffice, and we'll set up separate node pools for our various experimental configurations. Consequently, the default node pool can be minimal in terms of both node count and machine size. For instance, we can keep the E2 medium, which will be mainly used for system configurations or other supplemental testing tasks. Additionally, we need to ensure access to all cloud APIs. If you're using these notebooks for experimentation, ensure that they can interact with the wide array of Google Cloud services. We'll mostly retain the other default settings, aside from enabling Cloud TPU under Features, leaving the TPU address range unspecified. This doesn't imply that TPUs will be automatically provisioned or that you'll have to pay for them. It only means that you can apply resource limits and pod annotations in your pod specifications to automatically provision and attach TPU nodes like TPU v2 or TPU v3. Once the cluster is ready, we'll transition to an IDE to begin setting up our notebook and hardware configurations. So we're creating a new GitHub repository here that we'll share in the description of this video. We're going to use commands to create our node pools for testing since we want to have good configurations tracking. Let's start off by creating a baseline node pool for our notebook without any accelerators, and then we'll explore how to run the notebook on that and test out performance. The command here is just creating a node pool with a single node with the machine type of N1 standard 16, which is 16 cores of CPU and 60 gigabytes of RAM. We're attaching that to our cluster and then specifying a node location. Now, as that gets created, let's go ahead and get started on our resources file, which will be used to run our notebook. The great part about this resources approach, and what we really love about this architecture, is that you can use the same notebook and just transfer it between hardware configurations quite easily, since Kubernetes provides an abstraction above the infrastructure itself. We're able to take advantage of that to have zonal and configuration agility, and you'll see that in just a little bit here. So our deployment has a notebook resource. We have some code commented out for different accelerator configurations, and specifically, we're going to give this notebook 8 CPUs and 48 gigabytes of RAM with 10 gigabytes of ephemeral storage. We're going to run this notebook in a private way without exposing a public IP, and so we'll skip token-based authentication. We're also persisting our data in a regional SSD storage disk, so this is a nice little hack here, and it allows us to move between all these different zones very easily with the same notebook and the same data in that notebook. Let's go ahead and get the credentials for our newly created cluster and then apply these resources. We know, given the CPU and memory needs, that this is going to land on the baseline node pool that we just created. We do a get nodes, and we can see that new node pool and our small default node pool, which was, again, just a little bit of backup for any supporting services that we might need. If we look at the console or through CLI commands, we can see that our default pool has about 1 CPU available and 3 gigabytes of RAM, and it looks like we're already starting to allocate some of our CPU and memory for that notebook in the baseline node pool. The container is creating here, so we'll be able to kubectl port forward to securely access that notebook shortly. All right, and with our notebook now running, let's do that port forward. We're going to supply the pod name here and then the address to run on our local machine, which will then be matched to the port on the notebook pod. These official Jupyter Docker images run on port 8888 by default. Running this additional address argument means that we can access this from a host other than localhost, but again, this is internal. In your own IDE, if that's running locally, you should be able to access this through localhost. This working directory is going to be persisted because we have mounted that persistent volume there. So again, we'll have some nice data persistence. Now I'm just going to bring in some example code that we can use to demonstrate these concepts. This is going to be a CSV file and then a Python notebook that analyzes the data and does a regression. You can get this benchmarking Jupyter notebook and a data generation script from the GitHub repository. Now, if your IDE or development environment is using things like proxies in front of your Jupyter environment, when you do this kubectl port forwarding, just add an allow origin argument to the notebook app. But in any case, once you have the data and notebook files, you can get started with the benchmarking. We'll show the concept with the baseline node pool and then quickly shift to GPU-powered configurations to check how our code performs across different hardware configurations. In the notebook, we'll need to install the latest NVIDIA driver and the JAX library. Then we'll calculate times for a cubic regression across both NumPy and JAX, with the idea being that when we try out hardware accelerators, we want to make sure we're using a framework like JAX, TensorFlow, or PyTorch that can actually take advantage of that GPU compute. Let's run through the cells here. Note that we're going to use the same cells in this notebook every time, but feel free to skip the GPU libraries installation for configurations that don't need them. We'll probably want to restart the kernel before we run our import since we just installed some libraries. The JAX default backend here just sanity checks what backend we're using so that if we have a GPU, we can know that we're actually using that GPU in the cubic regression. We're also just doing a single run and a single loop, particularly on the JAX side, since we want to avoid using cached calculations. Now, we probably want to capture these metrics and compare them. Since regression and experimental design aren't the focus of the video, we won't spend too much time on this, but you will need to grab the results as you go through your own use case. Now, let's highlight something really cool, which is that with just a couple of quick steps, we can switch to a different configuration as far as our experiments are concerned. For example, we could try out the latest L4 chip from NVIDIA with a similar CPU and RAM configuration as before and see how that affects our results. We're using a G2 Standard 16, which has 16 CPUs and 64 gigabytes of RAM. We're trying to keep things consistent by allocating the same amount of CPU and RAM each time, but keep in mind that you have really two levels of resource specification here, at the node level and then at the pod level. By default, the pods won't take advantage of all the resources on the node. We're also specifying the L4 accelerator type, and we can go ahead and create this resource. Once we have this new node pool created, it's really important that we tear down our old node pool or at least scale it down to 0 so that we're not paying for that compute. This is extra important when using expensive accelerators. We need to scale down the resources that are consuming those GPUs or TPUs down to 0 so that the associated node pool costs drop back to 0. And once that node pool is ready, we can either, through the console or through commands, bring down our old node pool by resizing it down to 0. We do have our L4 running, and the magic here is that if I run a get pods command, we'll see that it's being rescheduled onto that new pod. Now I actually do need to make one correction here, and that's that we must request the GPU in our pod configuration. We won't just get that by default, so let me revise that. We'll reapply our resources and then we'll have that new pod come up in the new node pool. As we talked about before, we have our data that we can use across any zone in this region and any of these compute configurations. So by providing this resource limit for NVIDIA GPU counts and the specification of a GKE accelerator, we're now going to be able to schedule that pod on our new node pool. To ensure that the GPU driver is present at the node level and that we're using the latest one, we'll explicitly add a driver installation here. This is nice if we're not using the automatic driver installation in GKE. In some ways, we need to have drivers installed at two levels, the infrastructure level and our notebook level. To further showcase the infrastructure agility here, we can do another quick switch to A100s, for example. If a zonal change was required, we simply need to change the node location setting. Again, remember to tear down the node pools that we don't need with the resize operation. And just to demonstrate how we can run our benchmarks with the GPU capabilities, let's do a port forward and run our notebook. As you can see from our default backend on JAX, we're now using the GPU in that calculation. We'll provide all the code that we walked through in the description of this video, and we'll also keep an eye on the comment section for any questions. Thank you for watching, and please enjoy responsibly.